live stream this Saturday. I'm calling it Saturday Science Day because we're going to continue our science and physics discussion from last night. And we will begin our black holes example and journey today. Here is Baji. He is currently not looking into the camera, but that's okay. He is relaxing. We've had quite a day with eating, sleeping, napping. We did the dishes. We went swimming. Baji has been holding the fort down, and currently he is in his relaxed position. And here is Fuji and Suji. Let me make sure that the live is shared with our friends and that many of our friends are hopefully able to join us tonight. How are you guys? And welcome, welcome. There we go. Hi, Suji. Suji is giving special kisses. She was over in the other direction, but now she's here. So let's see. Okay, good. I see my live on my channel. Just want to make sure. There we go. Hello. Thank you for joining. How are you? We are live, and because we had so much fun last night covering the physics topics and discussing and reading the book Einstein's Cosmos by Michio Kaku, we're going to continue that journey today. We are going to be continuing to continue from that chapter, from that topic, and from that discussion. So welcome, welcome. Thank you for being here. Let me make sure I type a few messages and welcome everybody, and then we'll get started with the book and with our discussion. Yay. How is everybody? Hi. I see a few people. Hello. Thank you for joining. Say something in the chat so I know you're here. Thank you. Thank you so much for being here. I see a few people. Thank you so much for being here. Give me just a second and we will get started with our discussion. All right, so basically last night, the discussion that we were having, first of all, we were reading from this book, Einstein's Cosmos by Michio Kaku. Hopefully you can hear us right now. So we were discussing Einstein's Cosmos by Michio Kaku. Here is Suji and Baji. And this is the book that we've been reading. And we actually finished quite a few chapters of this. We've been reading this and also accompanying this with some discussion of our own, using sort of my background in physics and some of the context that I can provide with these topics. And we saw sort of the journey of Einstein following his very successful year of 1905 and his various accomplishments in that particular year, but also some of the sort of tumultuous time in his personal life following that time of the success with special relativity and photoelectric effect. And after that, he also kept working because he realized about the limitations of his theory. He also realized that the theory needed to be kind of generalized more and also work for frames of reference where there's acceleration. Hi, Madeline. How are you? Hi, Madeline. Madeline is one of our VIP guests and she has joined, so that is really exciting. Thank you for being here. So, as I was saying, Einstein decided that he needed to kind of make his special theory of relativity more general and also work for frames that weren't just inertial frames of reference, but things that may have acceleration because our everyday life is very much something that has acceleration, gravitational acceleration. We're all kind of experiencing that. So something that would be able to be generalized to including these types of scenarios would be better. And so that was his motivation to work on general relativity, and we covered that and how that all worked out. Oh, good. Time in Germany is 3:50. Oh, it's 3 in the morning, or 4 in the morning now. Goodness, Madeline, you're up late. But actually, yes, some people actually mentioned last night that it might be good to start sort of at this late time. Some people actually stay up late and they appreciated the late live, so I decided to go live now. But anyways, kind of going on, I'm summarizing what we covered. So we covered, let's see, we are on chapter 6 now. We have already covered up to chapter 5, and it was a very interesting discussion that we were in the middle of from chapter, let's see, chapter 6, because we talked about, let me sort of recap a little bit here. So we already talked about how the expansion of the universe was something that was starting to dawn on people. Basically, Einstein realized that he kind of was faced with the same challenge that Newton had been faced with, which was that if everything was undergoing an attractive force of gravity, why isn't the universe kind of collapsing on itself? So they needed something to counter gravity in order to explain that the universe is staying static. So he basically introduced a cosmological constant or a fudge factor to keep the universe sort of stable and static and nice. But then that gave rise to sort of this possibility of, well, because the cosmological constant is a fudge factor, it's a mathematically inserted quantity, well, we can actually change it. We can imagine it being some other value or some another value and things like that. And that's where sort of the universe's expansion or contraction or something like that, people decided to think about it as maybe contracting could be possible or maybe expanding could be possible. And all these types of theories started to rise, and also people related the density of the universe with maybe it's contracting or expanding, and all these different math variables that you could kind of play with in order to come up with a new reality for the universe. So, having having done this, this kind of gave rise to this work in cosmology, and it even became sort of a field because you could think about the cosmos in these different ways. And until you have some sort of like observational evidence pointing towards a certain type of actual reality, you could kind of keep playing with the numbers and the math as much as you pleased. And you could even come up with sort of alternate possibilities, let's say. So then, actually, Hubble, this astronomer that is very famous, his work and contributions, again, very, very famous, he actually helped to see a completely new world. Hi. Yes. Remember Gensh? Yes. I do remember Gensh. Yes. I just saw your comment. Sorry about that. Hi. Yes. Gensh as in goose. I do remember. Hi, Hunter. Hi, Alia. How are you? Hi, everybody. Alia says, who wants to be friends with me? Of course, all of us, how are you doing? How are you doing? Hunter, hi. This is Suji. I wanted to show you, here is Baji, here is Suji. How are you doing? What a nice cat. Thank you, Hunter. Thank you so much. How are you guys? I'm sick. Oh no, what happened, Madeline? Oh, that's too bad. Yes, we want to be your friend, Alia. Thank you. Hunter says, I love cats. Oh, thank you so much. Here, take a look at Baji. He is over here. He's very sleepy right now, but that's Baji and Suji. Madeline, what kind of, hopefully you're recovering well. Feel better soon. I was going to say, what kind of sickness is it? Hopefully it's nothing too bad and you recover soon. Yeah. So I'll get back to the sort of chapter that we were on. Hi, Madeline. How are you? Yay. Thank you, Alia, for asking. Yes, please do get to know each other better in the chat and welcome any conversation from you and love to see your comments and chat messages and love to catch up with you. And I will do so in between the reading and the discussion for sure. So stick around, settle in for the live stream. Thank you once again for being here and we will continue with our topic here, which is chapter 6 of The Big Bang and Black Holes from Einstein's Cosmos by Michio Kaku. So I was explaining how the cosmological constant came to be, and it kind of gave rise to these other sort of realities and possibilities for the universe. But really, it was the observational evidence that kind of made the deal as far as what we then came to understand about the universe. And we also discovered that there were other galaxies. So this was a big deal as well. We did not know prior to this time in the 1920s and 1930s that there were, in fact, multiple galaxies, lots of galaxies beyond our own galaxy. So that too was something that we knew now. I'm a head out. Bye, everyone. Bye, Alia. Thank you so much. I don't know, but I'm coughing very loud. Oh gosh, Madeline. Well, I hope that many of you will stick. Yes, I'm talking about astrophysics. Yes. Yes, indeed. So we are covering physics and astrophysics and cosmology, actually, as part of this live stream. So if you want to stick with us, you might learn something and kind of aid in our discussion. We can chat together for a while here. So let me start reading, and that might help with our discussion because that'll kind of ground our conversation in some facts, and then we can jump in with other topics and discussion. I think I'll stay because I love cats. Talk about neutron stars. Got it. Okay. Did the universe have a beginning? Is the universe finite or infinite? Will it have an end? As he began to ask what his theory might say about the cosmos, Einstein, like Newton before him, encountered the same kinds of questions that had puzzled physicists centuries earlier. In 1692, 5 years after Newton completed his masterpiece, Philosophy Naturalis Principia Mathematica, he received a letter from a minister, Richard Bentley, that perplexed him. Bentley pointed out that if gravity was strictly attractive and never repulsive, then any static collection of stars will necessarily collapse in on itself. This simple but potent observation was puzzling as the universe seemed stable enough, yet his universal gravitation would, given enough time, collapse the entire universe. Bentley was isolating a key problem faced by any cosmology in which gravity was an attractive force. A finite universe must necessarily be unstable and dynamic. So, see how Newton also had to deal with this issue of a static universe in which gravity was playing such a big role. But if it's an attractive force, then why doesn't it all collapse on itself? So, this was the very difficult question that he had to think about as well. And the same thing you will see, this was in the 1600s, but the same thing you will see comes back in the 1900s when Einstein comes up with his updated theory of gravitation, which is basically the theory of general relativity. After pondering this disturbing question, Newton wrote a letter back to Bentley, stating that the universe, to avoid this collapse, must therefore consist of an infinite, uniform collection of stars. If the universe were indeed infinite, then every star would be pulled evenly in all directions, and hence the universe could be stable even if gravity was strictly attractive. Newton wrote, if the matter was evenly disposed throughout an infinite space, it could never convene into one mass, and thus might the sun and fixed stars be formed. Yeah, go get a coffee. My birthday is on 25/12. Oh, so December 12th? Wow, that's awesome. So basically, it was sort of a way to keep the peace within the universe, if you will, because Newton is saying, well, maybe there's a very uniform and homogeneous collection of stars, and every star or every object in the sky is being pulled uniformly in every direction. So there's not anything sort of collapsing on itself. The universe and the collection of stars and other objects are not sort of collapsing upon itself because there is this pull from every direction. So he kind of basically he said what he had, the only logical thing that probably came to mind, but it was not really it was kind of a simplistic solution. I think because things were so difficult back then, especially with, observations and astronomy of faraway objects, like it was really difficult to do all these observations back in the day. And so, whatever logical explanation one could give is what he basically suggested. So, but if one made that assumption, then there arose another deeper problem known as Obler's paradox. It asks quite simply why the night sky is black. If the universe is indeed infinite, static, and uniform, then everywhere we look, our eyes should see a star in the heavens. Thus, there should be an infinite amount of starlight hitting our eyes from all directions, and the night sky should be white, not black. So if the universe was uniform and finite, it would collapse. But if it were infinite, the sky should be on fire. So, thank you, Hunter. So basically, this kind of gave rise to some more confusion, and people didn't really. I feel like in the 1600s or even in the 1900s, we weren't really ready with the observational power that we have now in astronomy to really answer these questions about the universe, because no matter what you kind of theorized, you'd have to back it up with some kind of evidence to really show. That that was the truth, or at least have some bits and pieces of truth come in the form of observational evidence, which is much more possible in the last 100 years, in the last few decades, especially where we've made leaps and bounds in observational abilities. But back then, these were all just kind of theories as to why, what was the nature of the universe, why things were not collapsing on itself. So it's still just theories. So now we come to the time of Einstein. So remember, Einstein was doing his work with general relativity, and with special relativity was in the early 1900s, and then he wanted to generalize it to general theory of relativity, and that was really in the sort of 1920s timeline. And in the 1920s is also when he won his first, his only Nobel Prize. So over 200 years later, Einstein faced the same problems, but in disguised form. In 1915, the universe was a comfortable place, thought to consist of a static solitary galaxy, the Milky Way. So just imagine this. In 1915, we thought that there was just the one galaxy, our galaxy, which is the Milky Way. We did not know that there were other galaxies as well, that there were actually billions of galaxies, lots and lots of other galaxies out in the sky. Now with our observational advances, we know about that, but back in 1915 they did not. So yeah, this in 1915 the universe was a comfortable place thought to consist of a static solitary galaxy, the Milky Way. This bright swath of light cutting across the night sky consisted of billions of stars. But when Einstein began to solve his equations, he found something disturbing and unexpected. He assumed that the universe was filled with a uniform gas which approximated the stars and dust clouds. Much to his consternation, he found that his universe was dynamic, that it preferred to expand or contract and was never stable. In fact, he soon found himself in the quicksand of cosmological questions that have puzzled philosophers and physicists like Newton for ages. Finite universes are never stable under gravity. Basically, if you make the universe finite, then it does not remain stable under gravity. We would, we humans are too new in this universe. That could be, yeah. So Einstein, forced to confront a contracting or expanding dynamic universe like Newton, was still not ready to throw out the prevailing picture of a timeless, static universe. Einstein, the revolutionary, was still not revolutionary enough to accept that the universe was expanding or had a beginning. His solution was a rather feeble one. In 1917, he introduced what might be called a fudge factor into his equations, the cosmological constant. So the cosmological constant is in quotes here because that's what people, that's what he called it. That's what maybe he called it or people called it around that time. But even now, we talk about this. That sort of nomenclature has stuck around, and we still call this cosmological constant, this factor, this sort of thing you needed in the math to make the math work out. Basically, this factor posited a repulsive anti-gravity, so it would work against gravity, that balanced the attractive force of gravity. The universe was made static by fiat. So basically, this is what was... Yes, fudge factor. This was basically a factor, sort of like a variable that you can put in, or really a cosmological constant would be more like a constant, but like give it some name, maybe capital C, which was put in to make the universe kind of work out and be stable and finite and static, because he knew that something had to be working against the gravity to make things not collapse. So he put that in, and the author here is calling it a feeble attempt to keep things sort of, stable in the universe. But at the same time, it wasn't bad that Einstein did that. At some point, you might kind of hit up against a wall and you just don't know. Like, you don't know the answer, but you have done enough math to describe the universe. So the part that you don't know, maybe you just call it C, in this case, which stood for cosmological constant, but maybe you just put a factor in and a placeholder, if you will, to kind of say, well, I don't know what that is, but there has to be something. And because he suggested that there has to be something, it actually led to a lot of other more follow-up work. Because remember, Einstein is not the only person who is working on all these types of problems. There are other physicists, other scientists who can contribute. And when you have something like this, like you say, it's a placeholder, well, it makes other people curious and want to contribute. And you're actually creating an opportunity for other people to contribute. So that's actually what he did there. So to perform this sleight of hand, so people are calling it, the author is calling it sleight of hand because it's literally sort of something like made up. It's like a constant. You put that in to make the equation work out. Einstein realized that general covariance, the main guiding mathematical principle behind general relativity, allows for two possible general covariant objects, the Ricci curvature, which forms the foundation of general relativity, and the volume of space-time. So it was therefore possible to add a second term to his equations that was consistent with general covariance and proportional to the volume of the universe. So he basically kind of even got a sort of a type of thing that this fudge factor might be, because he knew his equations, and because he knew exactly where he's putting in the constant, and he has other things in the equation and other types of things like the units of things. He can kind of even guess at what type of term it would really have to be. It's almost like the rest of the math is kind of defining out what this cosmological constant has to be. There is a vampire. Thank you. Great. In other words, the cosmological constant assigned an energy to empty space. So now this is very important. This is very important. Basically, by doing this math, he had assigned an energy to empty space. This anti-gravity term is now called dark energy. So this is a question that we still have. We still don't know what is dark energy, but this is kind of how it got started. So I thought it would be very interesting to share this with you, where we kind of understand where this concept of dark energy is coming from. It's literally it's literally physicists trying to make things make sense, and some of the things they know and some of the things they don't know. And that's actually how science kind of works. You just kind of try and you guess at things and you try to prove things out, and sometimes you come up with a really good theory, and then you have to back it up with evidence from observations, and then you just kind of see where everything falls. And sometimes your theory can be something that you have a lot of confidence in because it just seems to make a lot of sense, and then sometimes it just kind of comes into play because that's how things play out. It's not necessarily something you were expecting. So I think this particular cosmological constant phenomena is something that it's something that they had to kind of come up with or insert because they needed to. It wasn't necessarily something that they understood physically. It's not like, even now, we don't really know exactly the physical quantity or the physical meaning of dark energy. And that's the big concern even now. The fact that we kind of don't really know what dark energy is one of the top questions. So I thought, our generation, the people now in our contemporary world, we should know what the top questions of the universe are, and dark energy is one of them. The top 3 questions are dark energy, dark matter, and origin of elements. And, well, at least some of the elements are not known exactly what process made them. So I thought that this is really nice. It's giving us an introduction to dark energy. So we'll keep reading. This anti-gravity term, now called dark energy, is the energy of the pure vacuum. It can push galaxies apart or bring them together. Einstein chose the value of the cosmological constant precisely to counteract the contraction caused by gravity, so the universe can become static. He was unhappy with this, as it smacked of a mathematical swindle. But he had no choice if he wanted to preserve a static universe. So, he wasn't a big fan of doing math to make math work. Sort of like this cosmological constant, because it came about without really knowing its physical meaning. It was needed by the equation, so he kind of did it. And also it was needed by common sense, but we didn't know what it was really, and we still don't know. And so he wasn't exactly thrilled with it. And that's part of life too, is that we don't, sometimes our work, there will be parts of it that we don't really like all that much. It's just something that we have to do. It's not like everything is thrilling. And I think this cosmological constant was something that he was not particularly thrilled about. Anyway, so he was unhappy with this, but he had no choice. It would take another 80 years, so that's 80 years, before astronomers finally found evidence for the cosmological constant, which is now believed to be the dominant source of energy in the universe. So 80 years later, we actually have evidence that the universe is not only expanding, but its expansion is accelerating. So a lot of significance is now given to this cosmological constant or dark energy. And significance, especially, I think it's also good to understand the significance of it is also that we simply don't know what it is. We've tried to figure out what it is, and there's theories about what it might be, and there's big collaborative efforts to figure out dark energy and what it is. Some of the current experiments that are working on this is the Dark Energy Survey and Dark Energy Spectroscopic Instrument, DESI and DES. I personally worked a little bit on DESI myself when I was in grad school, but as far as I know, there's still this is still an open question. It's an open mystery, a puzzle that we still haven't solved, which is what is exactly the nature of dark energy? What is the meaning of dark energy? Really, in physical ways, the physical sense of it is still missing. Hi again, Madeline. Thank you for being here. Thank you so much for joining. The puzzle deepened in the next few years as more solutions to Einstein's equations were discovered. So we will see that once you have equations, different people can apply them to different types of things and environments and examples that they can come up with. And the nice thing is when you've done a really good work, other people get inspired to also contribute and also to think of things, and that's all very good. That's all good to do, but that also means that more questions can kind of come up with this other additional work. So in 1917, Willem de Sitter, a Dutch physicist, saw that it was possible to find a strange solution to Einstein's equations, a universe that was empty of all matter, yet it still expanded. All that was needed was the cosmological constant, the energy of the vacuum, to drive an expanding universe. This was unsettling to Einstein, who still believed, like Mach before him, that the nature of space-time should be determined by the matter content of the universe. Here was a universe that expanded without any matter whatsoever, needing only dark energy to propel itself forward. So, imagine, you come up with, Hunter says he's from Canada, Ali is from Ohio, Madeline is from Germany. Very nice. Very nice. But imagine this universe theory that you've come up with, and it works, and you had to introduce a cosmological constant to make the equation balance out. And your theory is about gravitation, which is, has to do with matter and the attractive force between matter. Einstein described this as a bending of space-time, and the more massive the object, the more it would bend space-time. But now somebody, this Dutch physicist de Sitter, is saying that he can even make a universe work that doesn't even have matter. And actually, it was quite an interesting thought. It's very much in line with some of the progress that we have seen now, where the significance of... Oh, hi, Baji. See, Baji wants to sit on lap. Come, Baji. Boshpe. Bosho, Shona. Hi, Baji Baba. Look, Baji's here. Hi, baby. Oh, I'm glad everybody is talking about their birthday. Very nice. The Dutch always causing trouble. Yeah, so the Dutch physicist basically, because if you want to sit down and do some math, then why not? And you can even come up with all kinds of theories, right? And if the theory is not too crazy, if it is sort of consistent with what was being said, and you just had to shift a few things around, and mostly staying consistent with the theory, because if you're saying, okay, there is some matter and some dark energy, well, then what is to say that there's no matter and all dark energy, or maybe there's a very little matter and mostly dark energy? You can kind of play around with these terms. Of course, all of these playing is only until the evidence points differently. Like if there is a strong observational evidence to the contrary, then of course you wouldn't keep saying the same thing. But until such evidence came in, you could actually say anything you wanted, and kind of make it work. Baji, the little kitty. Yes, this is baby. This is Baji, baby. Shona. I like December. So, Madeline, your birthday's coming up next month. Very nice. I just had my birthday in October. Ole Baba. Shona Baji is going to sleep on my lap. So, anyways, so that's the Dutch causing problems that we just saw. But anyway, moving forward, the final radical steps were taken by Alexander Friedman. So this is another guy. This is, so we just saw the Dutch physicist's proposition. Now we have Alexander Friedman in 1922, and by a Belgian priest Georges Lemaitre in 1927, who showed that an expanding universe emerges naturally from Einstein's equations. So, oh, hi, Baji. Baji is listening so intently. Shona Chilito. So, this other guy, well, a couple of guys actually, they came up with a theory which actually supports an expanding universe and that it comes naturally from Einstein's equations. So I think Einstein, the way he did his work, he wanted to keep it a little bit conservative in terms of the universe expanding. He just wanted to have the piece with sort of gravity working out in the universe and still keeping the universe as tame as possible. But then other people sort of had. Oh, thank you. A kiss for Baji. Other people had even more creative ideas, such as Friedman and Lemaitre. So in 1927, these people showed that an expanding universe emerges naturally from Einstein's equations. Friedman obtained a solution of Einstein's equations beginning with a homogeneous isotropic universe in which the radius expands or contracts. Unfortunately, Friedman died in 1925 of typhoid fever in Leningrad before he could elaborate on his solution. In the Friedman-Lemaitre picture, there are three possible solutions depending on the density of the universe. So this is where they started to talk about the density of the universe and how that can have a relation to the type of universe that you get. So it gets very interesting. All these cosmological sort of gymnastics that they did in order to come up with a different theory for the universe was quite entertaining, actually. So, and something that we can all think about. It's not that, that you cannot imagine these things. Well, one can and should perhaps imagine alternate universes. So in the Friedman-Lemaitre picture, there are three possible solutions depending on the density of the universe. I'm just making sure I didn't press on something. Whoops, there we go. Okay, if the density of the universe is larger than a certain critical value, then the expansion of the universe will eventually be reversed by gravity and the universe will begin to contract. So if the density of the universe is bigger, then what that means is, the normal matter in the universe is the one that is affected by gravity, that the part of the universe that is affected by gravity is more than some critical value, and the universe should begin to contract. The critical density is roughly 10 hydrogen atoms per cubic yard. In this universe, the overall curvature is positive. By analogy, a sphere has positive curvature. So this would be kind of curving inward. If the density of the universe is smaller than the critical value, then there is not enough gravity to reverse the expansion of the universe, so it expands indefinitely. So in this case, basically, there is not enough matter or not enough of the stuff that is under gravity. And so, I hate to be contradictory. Okay. And so now you're saying that because of the cosmological constant, which allows for the universe to expand, the universe should actually be expanding indefinitely. Because I guess, the sort of inconvenient truth of the matter is if you introduce a cosmological constant once to kind of explain your equation and explain the state of the universe, it's not like it goes away, right? You're saying that that's what is countering the gravity force. Things are not collapsing on itself, so there must be this thing that's expanding. And also you can play with the density number for matter in the universe, which is under gravity. And so if that matter is less, or in other words, if the density of the universe is less than some critical value, then actually your other thing that you had to introduce to make things work in the first place, the cosmological constant or dark energy, it has to be sort of more free to just keep on expanding the universe. So it's almost like this inconvenience upon inconvenience is coming out of this thing, but you cannot do anything about it because you already introduced it, and there was a need for which you had to introduce it. And now we're in this state of affairs where we have to have a cosmological constant, and it is giving us inconvenient after inconvenient truth, if you will. And it's still actually the case. Even now, we don't know what this dark energy is. So I need more coffee. Okay, good. Also, I have my period for 2 months. For 2 months. Oh my gosh. Madeline, I hope you take care. So I thought this was funny, but also very real. The problems of science. It's not easy. So, anyways, those are the two cases. So, if the density of the universe is smaller than the critical value, then there is not enough gravity to reverse the expansion of the universe, so it expands indefinitely. Eventually, the universe approaches near absolute zero in temperature as it expands toward what is called the big freeze in this case. In this universe, the overall curvature is negative. By analogy, a saddle or a trumpet horn has negative curvature. Last, there is the possibility that the universe will be balanced right at the critical value, in which case it will still expand indefinitely. So, in this universe, the curvature is zero. What does Baji mean? Bye, Madeline. See you next time. Baji means... trying to get the right word. It kind of means firecracker in Bengali. In this universe, the overall curvature is negative, by analogy, a saddle or a trumpet horn. Lastly, there is the possibility that the universe will be balanced right at the critical value, in which case it will still expand indefinitely. In this universe, the curvature is zero, so the universe is flat. Thus, the fate of the universe could be determined in principle by simply measuring its average density. So this was sort of something that they drove towards, which is that, well, we could try to measure the average density of the universe, and see from that what its curvature is. What is the nature of the universe? Is it does it have a curvature, kind of like a sphere or kind of like a trumpet, or is it flat or zero curvature? So, progress in this direction was confusing since now there were at least three cosmological models about how the universe should evolve: Einstein's, de Sitters, and Friedmann-Lemaitre's. So, these three models are now under consideration. The matter rested until 1929 when it was finally settled by the astronomer Edwin Hubble. So we have Hubble, the astronomer I mentioned earlier, whose results were to shake the foundations of astronomy. So, at some point, the theories are all well and good, but you really need some observational evidence to kind of move the field along and to progress further in the topic. And this was provided by Edwin Hubble, thankfully. So he first demolished the one galaxy universe theory by demonstrating the presence of other galaxies far beyond the Milky Way. So this was earth shattering in the sense that we thought back in 1915 or 1920s that there's just the one galaxy, our galaxy. It's called Milky Way, and we did not know about the presence of lots and lots of other galaxies. So this came as a big shock. It was a big thing. He first demolished that. The universe, far from being a comfortable collection of 100 billion stars contained in a single galaxy, now contained billions of galaxies, each one containing billions of stars. In just 1 year, the universe suddenly exploded. So they've suddenly found, with the use of better telescopes, that the universe had more galaxies. It wasn't just our galaxy. So this was a very big deal. He found that there were potentially billions of other galaxies and that the closest one was Andromeda, about 2 million light years from Earth. Yes, Andromeda, very nice. The word galaxy, in fact, comes from the Greek word for milk, since the Greeks thought that the Milky Way galaxy was milk spilled by the gods across the night sky. So you probably knew that. This shocking revelation alone would have guaranteed Hubble's fame among the giants of astronomy, but Hubble went further. In 1928, he made a fateful trip to Holland where he met de Sitter, who claimed that Einstein's general relativity predicted an expanding universe with a simple relationship between redshift and distance. So, this is where something was going to happen that really moved astronomy in a new direction, and this concept of utilizing redshift as a way to measure things for us in astronomy started to be. So this is really interesting. So listen up. Basically, he suggested. So Hubble and his friends suggested the farther our galaxy was from Earth, the faster it would be moving away. This redshift is slightly different from the redshift considered by Einstein back in 1915. This redshift is caused by galaxies receding from Earth in an expanding universe. If a yellow star, for example, moves away from us, the speed of the light beam remains constant, but its wavelength gets stretched so that the color of the yellow star reddens. Similarly, if a yellow star approaches Earth, its wavelength is shrunken, squeezed like an accordion, and its color becomes bluish. So they're basically saying that we wanted to understand about expanding or not, right? Because de Sitter had suggested an expanding universe, remember, with the no matter and only dark energy. The other two people, Friedman and Lemaitre, I believe, also suggested expanding universe, but you kind of have to kind of prove that this is the case. How do you prove that the universe is expanding? So Hubble and these astronomers with the new astronomy instruments suggested, well, what if we measured redshift? And if we see the galaxies that are far from us to be receding, then we know that they are, going farther and farther away, and the universe is expanding. But if they're coming towards us, and we measure that by measuring its redshift, which would actually be a blue shift now because they're coming towards us, then we would know what was happening instead. That maybe the universe was contracting. So This was how they proposed being able to measure the expansion of the universe, which was really interesting and something that we very commonly use even now. This phenomena of the red shift and everything like that. So, anyways, when Hubble returned to the observatory at Mount Wilson, he began a systematic determination of the redshift of these galaxies to see if this correlation held up. Baji's in a ball now. He knew that back in 1912, Vesto Melvin Slipher had shown that some distant nebulae were receding from Earth, creating a redshift. Hubble now systematically calculated the redshift coming from distant galaxies and discovered that these galaxies were receding from Earth. In other words, the universe was expanding at a fantastic rate. He then discovered that his data could fit the conjecture made by de Sitter. This is now called Hubble's law. The faster a galaxy is receding from Earth, the farther away it is. So he was able to kind of show that these galaxies were receding, and because he can measure it with the redshift, he also knows that the faster, he also found that the faster the galaxy was receding from Earth, the farther away it was, and it became a new law, Hubble's law. Plotted on a curve, graphing distance versus velocity, Hubble found a near straight line as predicted by general relativity, whose slope is now called Hubble's constant. Hubble, in turn, was curious to know how his results would fit into Einstein's. Unfortunately, Einstein's model had matter, but no motion, and de Sitter's universe had motion, but no matter. Because remember, de Sitter had said that he could make Einstein's equation work with no matter. So he kind of got rid of the matter. His results did seem, because, when they were doing the math, they didn't necessarily have to consider the reality, whereas Hubble is in the, very much the reality. He wants to actually observe, and have experimental evidence of what is actually happening in the universe, which is very, very tough to do, but he was being quite successful with it. So anyway, his results did seem to agree with the work of Friedman and Lemaitre, which possessed both matter and motion. So thankfully, there was one concept, one cosmological model, which kept the matter as well as the motion, and that one was the one that seemed to agree the most with what Hubble was finding. So in 1930, Einstein made the pilgrimage to the Mount Wilson Observatory, where he met Hubble for the first time. Wow. When the astronomers there proudly boasted that their mammoth 100-inch telescope, the biggest in the world at that time, could determine the structure of the universe, Elsa was not impressed. She said, "My husband does that on the back of an old envelope." As Hubble explained the painstaking results he found from analyzing scores of galaxies, each one receding from the Milky Way, Einstein admitted that the cosmological constant was the greatest blunder of his life. The cosmological constant, introduced by Einstein to artificially create a static universe, was now dispensable. The universe did expand, as he found a decade earlier. So basically, he's thinking that this cosmological constant that he introduced to balance things out with the universe was a blunder. But actually, it was nice in the sense that it kind of gave rise to all these different competing theories, and people started to really scratch their heads and try to understand about this other stuff in the universe that might be the one that is balancing gravity. And because they were trying to balance gravity, they basically realized that the universe was expanding. So it was still very useful to do it, and it's something that is still being probed even today. And we still don't know, we still don't really have the explanation of why exactly physically the universe is expanding, what is making it do so, and what is this dark energy. Right. So I wouldn't say that it was a waste. It was just simply a work in progress. Even Einstein's work can be a work in progress sometimes. Furthermore, Einstein's equations gave perhaps the simplest derivation of Hubble's law. As assume the universe is a balloon that is expanding, with the galaxies represented as tiny dots painted on the balloon, to an ant sitting on any one of these dots, it appears as if every dot is moving away from it. Likewise, the farther a dot is away from the ant, the faster it is moving away, as in Hubble's law. Thus, Einstein's equations gave new insights into such an ancient question like, is there an end to the universe? If the universe ends with a wall, then we can ask the question, what lies beyond the wall? So things like that. There were a lot of sort of philosophies and physical understandings of the universe that was getting shaped by this. So one more example that I'll point out is, so basically people were questioning whether the universe is finite or infinite. And it turns out that kind of depends on how you're thinking of the universe. The universe might be finite in some dimension, but it is infinite in our three dimensions. And you can think of it as the Earth. The Earth is both finite and infinite at the same time, depending on the number of dimensions one measures. For example, if in three dimensions, the Earth is finite, being just a ball floating in space, but in two dimensions, it appears infinite if one goes around and round its circumference. So anyone walking on the surface of the Earth will never find the end. So that's sort of an analogy to say that the universe is sort of similar in the sense of, depending on how many dimensions you're measuring with, it can be either finite or infinite. The way we know it, in the three dimensions at least, it seems to be infinite. Universe is infinite in three dimensions. There's no brick wall in space that represents the end of the universe. A rocket, if sent into space, will never collide with some cosmic wall. So, but as far as, is there is there a way in which we might say that the universe is finite? There is a possibility that the universe might be finite in four dimensions. If it were a four-dimensional ball or hypersphere, you might conceivably travel completely around the universe and come back to where you started. In this universe, the farthest object you can see with the telescope is the back of your head. So basically, there were these types of debates and sort of gymnastics in trying to understand the universe. If the universe is expanding at a certain rate, then one can reverse the expansion and calculate the rough time at which the expansion first originated. So not only were there these questions of whether the universe is finite or infinite, but because now we kind of had measured the expansion of the universe, it also allowed for people to basically think about the origin of the universe, which is that, well, if it's expanding, then we can just go back in time and see where it started, how it started, right? So that's basically how the theory for the Big Bang came to be. So in other words, not only did the universe have a beginning, but also one could calculate its age. So in 2003, satellite data showed that the universe is 13.7 billion years old. In 1931, Lemaitre postulated a specific origin to the universe, a superhot genesis. If one took Einstein's equations to their logical conclusion, they showed that there was a cataclysmic origin to the universe. In 1949, cosmologist Fred Hoyle christened this the Big Bang theory during discussion on BBC Radio. Because he was pushing a rival theory, the legend got started that he coined the name Big Bang as an insult, although he later denied that story. However, it should be pointed out that the name is a complete misnomer. It was not big and there was no bang. The universe started out as an infinitesimally small singularity, and there was no bang or explosion in the conventional sense, since it was the expansion of space itself that pushed the stars apart. Not only did Einstein's theory of general relativity introduce entirely unexpected concepts, such as the expanding universe and the Big Bang, but it also introduced another concept that has intrigued astronomers ever since, which is black holes. So this is what we'll get into now, black holes. So up to now, we should take a minute to appreciate that Einstein's theory of general relativity, and even though he called the cosmological constant his blunder, but actually it's really it really did progress the field in the sense of like, well, because of that, we had to start thinking about what was this cosmological constant, what did it stand for, the concept of dark energy and all these efforts to understand dark energy. It all kind of came to be because we had this updated theory of gravitation and of the universe, and we needed this other thing to explain why the universe did not collapse. And it kind of led to the complete opposite problem, which is that the universe was expanding. And now we know for sure the universe is expanding because even there were measurements. Not just that, we actually even later on confirmed that the universe was not only expanding, but its expansion is accelerating. So confirming all of this is a very big deal. And it all came to be with this work of general relativity and his equations needing that. But even though we still don't know exactly the nature of dark energy, it is important to understand sort of where we are and what we don't understand, you know? So that's what's important here. And also, we were able to postulate something for the origin of the universe, this whole concept of Big Bang. Because the universe ended up being something that is expanding, we were able to kind of track that back and get the origin of the universe. We called it Big Bang, even though really it was a singularity and maybe a small, not big but small, and not bang but a singularity that it all started with. But those types of concepts were really not there before this work of general relativity. That's why we must thank Einstein for his work. And even if some of it was a little bit awkward, it still progressed the field. And also, now we will get into black holes, which is actually a really interesting topic because the nice thing with black holes is that they are a very extreme type of object in the sky, which gives us a very natural playground and sort of an environment to test out these types of theories like the general theory of relativity and any equations that you want to try out on a black hole. Well, a black hole is a great type of object to try this out on because sometimes when you have a theory, being able to test it out on a very extreme case is important because there's a lot to learn there. And also, if it doesn't work for the very extreme case, then you can kind of do away with the theory and be like, well, it doesn't really work. So black holes is exactly that type of playground. In 1916, just 1 year after he published his theory of general relativity, Einstein was astonished. Excuse me, 1 second. I have a little bit of cat fur in my mouth. In 1916, just 1 year after he published his theory of general relativity, Einstein was astonished to receive word that a physicist, Carl Schwarzschild, had solved his equations exactly for the case of a single point-like star. Previously, Einstein had only used approximations to the equations of general relativity because they were so complex. Schwarzschild delighted Einstein by finding an exact solution with no approximations whatsoever. So because his equations were so complicated, he generally had to use approximations. But what if you could solve them exactly for a type of object? And what if that type of object actually kind of existed? So Schwarzschild did this for a case which was like a single point like star. And it so happens that it kind of worked out for something like a black hole. Although Schwarzschild was director of the Astrophysical Observatory in Potsdam, he volunteered to serve Germany on the Russian front. Remarkably, as a soldier dodging shells bursting overhead, he managed against all odds to work on physics. Not only did he calculate the trajectory of artillery shells for the German army, he also calculated the most elegant, exact solution of Einstein's equations. Wow. Today, this is called the Schwarzschild's solution. Unfortunately, he never lived long enough to enjoy the fame that his solution generated. One of the brightest stars emerging in this new field of relativity, Schwarzschild, died at the age of 42, just a few months after his papers were published, from a rare skin disease he picked up while fighting on the Russian front, a waste for the world of science. Einstein delivered a moving eulogy for Schwarzschild, whose death only reinforced Einstein's hatred of the senselessness of war. Oh, Baji. The Schwarzschild solution, which created quite a sensation in scientific circles, also had strange consequences. Schwarzschild found that extremely close to this point-like star, gravity was so intense that even light itself could not escape, so the star became invisible. This was a sticky problem not only for Einstein's theory of gravity, but also for the Newtonian theory. Back in 1783, John Michell, rector of Thornhill in England, posed the question whether a star could become so massive that even light could not escape. His calculations using only Newtonian laws could not be trusted because no one knew precisely what the speed of light was, but his conclusions were hard to dismiss. In principle, a star could become so massive that its light would orbit around it. 13 years later, in his famous book Exposition du Système du Monde, mathematician Pierre Simon Laplace also asked whether these dark stars were possible, but probably found the speculation so wild that he deleted it from the third edition. So these dark stars, quote unquote, are going to be black holes, and it's so interesting. People had kind of theorized about the possibility of their existence, but they do actually exist. And we found that centuries later. So, centuries later, the question of dark stars came up again, thanks to Schwarzschild. Now, because Schwarzschild worked with Einstein's equations and solved them for a point-like star, this question of dark stars, because if a star is point-like, as in it's very compact, well, is it going to be dark? Is it something that traps light, basically, where its light even just revolves around it? This whole physical reality of the dark stars and the black holes came about. Something that had been asked by people, beforehand, but the concept of dark star just seemed so, I don't know, so too extreme, I guess, and that's why people kind of abandoned it. But it came up again, and especially as Schwarzschild actually applied Einstein's equations to a point-like star and solved his equations exactly rather than with approximations, it was all kind of coming together. And, before you know it, we have more evidence and more knowledge about dark stars. So he found that there was a magic circle. He found that there was a magic circle surrounding the star, now called the event horizon, at which mind-bending distortions of space-time occur. So this is Baji is snoring. This is very interesting. He found that there was a magic circle surrounding the star, now called the event horizon, at which mind-bending distortions of space-time occur. Schwarzschild demonstrated that anyone unfortunate enough to fall past this event horizon would never return. You would have to go faster than the speed of light to escape, which is impossible. In fact, from inside the event horizon, nothing can escape, not even a light beam. Light emitted from this point-like star would simply orbit around the star forever. From the outside, the star would appear shrouded in darkness. One could use the Schwarzschild solution to calculate how much ordinary matter had to be compressed to reach this magic circle, called the Schwarzschild radius, at which point the star would completely collapse. For the Sun, the Schwarzschild radius was 3 kilometers, or less than 2 miles. For the Earth, it was less than a centimeter. So everybody has a Schwarzschild radius. This is the length that you would have to be compressed to in order to become a black hole. For the Earth, it's less than a centimeter. For the Sun, it's less than 2 miles. But basically, a very compact or compressed star that might have collapsed on itself after its death is what basically makes a black hole. It's a very compressed dark star, dark because even light cannot escape. And there is a circle around it, though, which Schwarzschild called the event horizon. And it was really this spot, which was you shouldn't fall past this one because it's really after that where you could not come back from. But even if you got close to a black hole, you would start to experience, so much stretching that would be very uncomfortable. But why it's important to understand event horizon and where the event horizon is and things like that is because, well, obviously, not everything in the universe has fallen into a black hole, right? A black hole might be something that lots of things have fallen into, and it's probably from a star dying and collapsing on itself and getting very compact to the point where it's a black hole. But there are things that generally will go around the black hole, right? And ultimately, those things might collide with the black hole and get sucked in. But before that point, they're not yet sucked in. So you might want to know exactly at what point you would get sucked in versus not, right? So I think those types of things are important to understand about the environment of a black hole and what's kind of going on around the black hole. And we've actually learned a lot since that time about black holes and what's around it. So one could use, oh yeah, we just talked about that. So since the compression factor was beyond physical comprehension in the 1910s, physicists assumed that no one would ever encounter such a fantastic object. Oh, so they still did not know about like real black holes back then. He solved Einstein's equation for a point-like star or a dark star, but these were just still kind of like words. They had not discovered actual, real black holes in the physical world yet. But the more Einstein studied the properties of these stars, later christened black holes, by physicist John Wheeler, the stranger they became. For example, if you fell into a black hole, it would only take a fraction of a second to fall through the event horizon. As you briefly sailed past it, you would see light orbiting the black hole that was captured perhaps eons, perhaps billions of years ago. The final millisecond would not be a very pleasant one. The gravitational forces would be so great that the atoms of your body would be crushed. Death would be inevitable and horrible, but observers watching this cosmic death take place from a safe distance would see an entirely different picture. The light emitted from your body would be stretched by gravity, so it would appear as if you were frozen in time. To the rest of the universe, you would still be hovering over the black hole, motionless. That's right, because beyond that, the light cannot escape. So you would just be seeing the light from where you're frozen. I'll read that again. The light emitted from your body would be stretched by gravity, so it would appear as if you were frozen in time. To the rest of the universe, you would still be hovering over the black hole, motionless, because, seeing you would be with light, and that's the light that is allowed to come out of the black hole. Everything else stays trapped, so we can't see your last moments, unfortunately, or fortunately. These stars, in fact, were so fantastic that most physicists thought that they could never be found in the universe. Eddington, for example, said there should be a law of nature to prevent a star from behaving in this absurd way. In 1939, Einstein tried to show mathematically that such a black hole was impossible. He began by studying a star in formation, that is, a collection of particles circling around in space, gradually pulled in by their gravitational force. Einstein's calculation showed that this circling collection of particles would gradually collapse, but would only come within 1.5 times the Schwarzschild radius, and hence a black hole could never form. Although this calculation seemed airtight, what Einstein apparently missed was the possibility of an implosion of matter in the star itself, created by the crushing effect of the gravitational force overwhelming all the nuclear forces in matter. This more detailed calculation was published in 1939 by J. Robert Oppenheimer and his student Hartland Snyder. Instead of assuming a collection of particles circling in space, they assumed a static star, large enough so that its massive gravity could overwhelm the quantum forces inside the star. For example, a neutron star consists of a large ball of neutrons about the size of Manhattan, 20 miles across, making up a gigantic nucleus. What keeps this ball of neutrons from collapsing is the Fermi force, which prevents more than one particle with certain quantum numbers, for example spin, from being in the same state. If the gravitational force is large enough, then one can overcome the Fermi force and therefore squeeze the star to within the Schwarzschild radius, at which point nothing known to science can prevent a complete collapse. However, it would be another 3 decades or so before neutron stars were found and black holes were discovered, so most of the papers on the mind-bending properties of black holes were considered highly speculative. So this stuff, black holes and neutron stars, you know, they thought that these were theories and that they could not be real. But this is actual science. We actually have seen black holes and neutron stars. And so we know that they do exist and that this is not a speculative theory anymore. We have evidence of this. So how strange, things like dark energy, dark matter, on the other hand, are still, we don't understand them. We don't know what makes them. What is the physical reality of these things? But dark stars or black holes is actually physical reality, and it is actually backed by observational evidence, and we have learned a lot about black holes since this time. But it's so interesting that sort of the theory of this came out of Einstein's general relativity being solved for a particular case by Schwarzschild, who didn't even really know about black holes. He just solved them for a point-like star and basically hypothesized that this could be some dark star that has compressed so much that it doesn't even allow light to come out of it. And it kind of all worked out. In fact, it gave us black holes, and we do actually have black holes in the universe. We have them in our galaxy. So they're not actually that special, turns out. We know that now, much, much later. Although Einstein was still rather skeptical about black holes, he was confident that one day, yet another of his predictions would come true, the discovery of gravity waves. So he was skeptical about black holes, but of course, black holes also came true. So that's a huge success, actually, of his theory. But he thought that there would be evidence of gravity waves, and we do have evidence of gravity waves. So as we have seen, one of the triumphs of Maxwell's equations was the prediction that vibrating electric and magnetic fields would create a traveling wave that could be observed. Likewise, Einstein wondered if his equations allowed for gravity waves. In a Newtonian world, gravity waves cannot exist since the force of gravity acts instantaneously throughout the universe, touching all objects simultaneously. But in general relativity, in some sense, gravity waves have to exist, as vibrations of the gravitational field cannot exceed the speed of light. Thus, a cataclysmic event, such as the collision of two black holes, will release a shock wave of gravity or a gravity wave traveling at the speed of light. So this is something that he predicted, that he was hoping that we would find. And guess what? We have actually found this. I think when this book was written, it was not observed yet, but we actually did find evidence of gravity waves within the last decade. So can you imagine, like, Einstein predicted this in the early 1900s, and we found evidence of this recently. So that's another huge triumph. He didn't think that we would find black holes, that there would be these things that are like point-like stars or dark stars or black holes, basically super duper compressed stars. He was thinking that those might not be real, but actually those too are real. Not only that, he predicted gravity waves, saying that in his theory of gravitation, gravity was carried by gravitational waves. It wasn't just an instantaneous force like what classical mechanics or Newton would have suggested. So then we should be able to kind of pick up on these gravity waves if we had a way to measure gravity waves, especially from a very big event like a big cataclysmic event like the collision of two black holes. And that's the exact type of event that we did start to look for. And we did start to try to measure the gravity waves from. And we did do this, by the way, in the last within the last several years. So we should read about LIGO, the experiment that works on this. But yeah, isn't that exciting? As early as 1916, Einstein was able to show that with suitable approximations, his equations did yield wave-like motions of gravity. These waves spread across the fabric. Sorry, I'm just making sure I got the right angle for Baji's. These waves spread across the fabric of space-time with the speed of light. As expected, in 1937, with his student Nathan Rosen, he was able to find an exact solution of his equations that gave gravity waves with no approximations whatsoever. Gravity waves were now a firm prediction of general relativity. So he showed, him and his student was able to find an exact solution of his equations that gave gravity waves with no approximations whatsoever. Gravity waves were now a firm prediction of general relativity. So it was he intended for them to be found. Basically, he's saying, I am firmly predicting gravity waves, and please, build some experiments that can actually pick up on gravity waves. And if you can do that, that would be a great triumph of general relativity and also a whole new understanding, of course, a firmness of the understanding of our universe. So Einstein despaired, however, of ever being able to witness such an event. Calculations showed that it was far beyond the experimental capabilities of scientists at that time. It would take almost 80 years since Einstein first discovered gravity waves in his equations for the Nobel Prize to be awarded to physicists who found the first indirect evidence of gravity waves. The first gravity waves may be directly detected perhaps 90 years after his first prediction. These gravity waves, in turn, may be the ultimate means by which to probe the Big Bang itself and find the unified field theory. In 1936, a Czech engineer, Rudy Mandel, approached Einstein with yet another idea concerning the strange properties of space and time, asking whether gravity from a nearby star could be used as a lens to magnify the light from distant stars, in the same way that glass lenses can be used to magnify light. Einstein had considered this possibility back in 1912, but prodded by Mendel, calculated that the lens would create a ring-like pattern to an observer on Earth. For example, consider light from a faraway galaxy passing by a nearby galaxy. The gravity of the nearby galaxy might split the light in half, which, with either half going around the galaxy, in opposite directions. How interesting. Wow. When the light beams pass the nearby galaxy completely, they rejoin. From the Earth, one would see these light beams as a ring of light, an optical illusion created by the bending of light around the nearby galaxy. However, Einstein concluded that there is not much hope of observing this phenomena directly. In fact, he wrote that this work is of little value, but it makes the poor guy happy. Aw. Once again, Einstein was so far ahead of his time that it would take another 60 years before Einstein lenses and rings would be found and eventually become indispensable tools by which astronomers probe the cosmos. So, this is yet another thing that not only did we find, but we actually use to probe the cosmos. And of course, his prediction of gravity waves, as I was telling you earlier, is also proved now. We did find gravity waves. It was actually a phenomenal observation, measurement, discovery, whatever you want to call it, in the last, within this last decade. I think it was 2015. I don't think it was earlier than 2015 when we saw gravitational waves. But don't quote me. Look up LIGO, laser interferometry, maybe gravitational observatory, something like that. It's LIGO, LIGO, is the name of the experiment that first picked up on the evidence for gravitational waves, and that was, a huge prediction of Einstein's general theory of relativity. So it was like amazing when that happened. Like I remember, like there were so many talks being given that the basically the press release of that event, of the finding, of the observation, of the measurement was like watched by all of us together. It was like this big public press release of the news of the finding of it and what it really meant. And, they basically looking for these cataclysmic events like black holes colliding or neutron star colliding. These types of events were predicted to produce these gravitational waves. We just needed a way to be able to measure it. And because it takes such precise measurement and it takes the building of such amazing instruments, precise instruments to be able to do that, basically astronomy and astrophysics has like moved by leaps and bounds in the last century in becoming much more precise and being able to make measurements that we would have thought would be impossible some time ago, 100 years ago or so. And so this was another example, a huge victory for general relativity. And then the thing with gravitational lensing, Einstein lenses that they thought about, which is the light from a faraway galaxy passing by a nearby galaxy, should split the light in half, with each half going around the galaxy in opposite directions and then creating an optical illusion by the bending of light around the nearby galaxy. This whole thing is actually used to do astronomy, to probe the universe, and so yet another prediction of Einstein having come true here. So, as successful and far-reaching as general relativity was, it did not prepare Einstein in the mid 1920s for the fight of his life to devise a unified field theory to unite the laws of physics while simultaneously doing battle with the demon, the quantum theory. So, after making predictions with general relativity and seeing a lot of that becoming successful, although a lot of it had to wait because we had to make the pertinent type of observatories or experiments to be able to measure it. Some of the measurements or some of the predictions did not get confirmed for decades just because he was so ahead of his time. But after working on general relativity and seeing it succeed to some extent, he was actually more interested in a grand unified field theory. And he wanted to bring all these sorts of like knowledge together in this unified field theory and battle the demon, the quantum theory. So we haven't talked too much about quantum theory in this book yet, but we will get into that, and we will look at his efforts to work on the grand unified theory as well. GUT. So the next chapter, so we just finished part 2 of this book. The next part, which will be part 3. Oh, sorry, Baji. Oh, Baji's just stretching. The next part is called the unfinished picture, the unified field theory. So it's important to understand what the effort was with the unified field theory. So we will definitely get into it. But also it's important to understand that Einstein had some struggles with it, and it's unfinished because he wasn't able to really successfully finish this theory. And it was still kind of unanswered. And that's why it's called unfinished picture. So it's important to understand that even the greatest people, greatest scientists of their time, can actually kind of struggle and have problems with making progress sometimes and figuring things out. And a lot of it is also that they're limited by what is available at the time, the observations that are possible at the time. And, we've mentioned how dark energy was a concept that came about when he was doing this work. And even now, today, we don't know what dark energy is. We just have observational evidence to confirm that we do need something like dark energy, but we just don't know what it really physically means. But we have confirmed the expansion of the universe, and we've confirmed, in fact, that the expansion is not only, expansioning, but it's also accelerating in its expansion. So understanding why that is and what this really means physically would be great, but we still don't know. And then the same thing is true for dark matter. This is another whole topic. Doesn't really come out of anything that we've talked about today so far or in the book so far, but there is another thing or a mystery, which is dark matter. We have evidence also of dark matter needing this other type of matter beyond ordinary matter to explain certain phenomena and certain observational evidence that we have found in the universe. So that is also another mystery. We don't know also what dark matter is. It's a placeholder term for something we don't understand. So it's important to understand that there are things that we know and understand and we made progress on. And along the way, we might have also opened up cans of worms or questions that are yet unanswered. And some of them are so difficult, sometimes because of how difficult it is to measure and observe and find the evidence for, and sometimes because it's just, I don't know, difficult in general, that we don't actually have the answer even now. So Einstein obviously has passed away. He's no more with us, and we don't have his great brain to help with these types of questions anymore. But even in his lifetime, he worked so much and he created so much, so many results and so many awesome predictions and theories and things like that that came true. But at the same time, he too had his struggles. So it can be difficult, for sure. It can be. So I think what we will do is next time we'll pick up from the unfinished picture, unified field theory. Hi, Baji. And we'll just take a little break now. And I'll catch up with your comments and chat messages if you send anything. Thank you for being here. Yes. Thank you, Heike. The Sagittarius system is definitely very interesting. It's a supermassive black hole in our own galaxy. Thank you for your comment. Thank you for reading. Happy Sunday to Baji and Science Book friends. Sagittarius A is a supermassive black hole in Milky Way. I should have named the live Sagittarius Saturday because Sag is our very own black hole. Hi, Ian. How are you? How are you doing, Ian? It was more quiet today. We had a really lively audience last night. We had lots of fun on the Physics Friday live. Today was good too, just more quiet, less people. But good to see everybody. Thank you for joining. Ian, Heike, Alia, Hunter. Who else was here that was chatting? Madeline, of course. Thank you. Thank you. Thank you. Baji. We missed you, everybody else that we could not catch. Maybe you'll watch the video replay and you can let us know your comments later on under the video. Thank you. Hi. I changed my user and profile because I'm a fan of anime. Oh. We like it, Ian. I like your new profile and name. It's nice. I'm just breathing in and out now. Hi, Kaki. Kaki Geprek of official says, "What kind of cat is that, sis?" He's a domestic short hair. He's currently hiding his face, apparently. Reese, we missed you. We've been in the live, and I was thinking that not very many people joined, and it's been very quiet. Reese, yes, you missed the live. Well, we're still here, but we just finished black holes. I know how to say domain expansion in JoJo form. Yon Stinky. Oh, no worries, Reese. I'm sure you were busy. Kaki Geprek says, I also have 2 cats. And an Angora and a Tortie. I actually have 3 cats. They're all domestic short hairs. Oh, that's good. I'm glad you fell asleep. Maybe, so are you in the middle of sleeping now? Maybe I started my live a little too late. Maybe I should start it a little earlier so that it's not so late. It's like midnight here in the US, so it's not too late yet. But I could start it a bit earlier so that people are not already sleeping. But you just woke up, so is it good morning for you, or are you going to go back to bed? It's still nighttime, right? I'm gonna put this down and get some water. Baji, can I get up, please? Baji, Mama wants to get some water. Here's Baji's face. Hi. I don't even know anymore. My sleeping routine is messed up. Oh, bliss. Yeah. Did you guys hear KSI new song? I don't think so. I don't think I know the new song, Ian. That's okay. I think I'll try out a little bit earlier time for the live and hopefully catch more people next time. We had a little bit of a crowd today, not too many people, much quieter. So I covered partially what I covered yesterday with the expansion of the universe. We kind of talked about that yesterday as well, but I figured if there's new people joining today, they wouldn't know about what we talked about yesterday, so I covered it again, and it's a very interesting topic. So we kind of talked about the expansion of the universe today, and then we had to finish the black hole part of the chapter still from yesterday, so I did that. So I finished up black holes. But we did not start the next chapter, which is unification and the quantum challenge. This is where Einstein is trying to unify all the field theories and come up with a grand unified theory. So this will be very important. You don't want to miss this one. So we're going to do this tomorrow. And hopefully everyone can join for that. It'll be a very important discussion. I'm in the think of it, everybody knows they know me. I was watching videos about the gravitational constant. I think tomorrow I can try to go live at like 8 or 9 p.m. Does that work? For the US Eastern Standard Time. And then in England, it'll be closer to like midnight. Okay. Yeah, I can try to go a little bit earlier so that I can catch everybody before they fall asleep in the US as well as the UK. Because, like, in the US, the, West Coast is still early. It's still early for them. Right. 11:25 for you, Ian. Yeah, I figured it's not like the most dead of night yet in the US. But if I go live just a little bit earlier, maybe 8 or 9 p.m. ish, a couple hours earlier than what I did today, that might be better for more people. Because I think because of the Sunday into Monday, people might be going to bed even earlier tomorrow. I'm not sure. I don't know what to do. My sleep schedule is a little bit messed up too. So I'm just trying things. How old are you? You mean me? I don't know, 13.7 billion years, approximately. What's my name? Baji's mom. You can't ask a lady that. You can't ask a lady that. You can, I mean, if you want. If you really want to, you could, I suppose. I don't know if it's gonna be very helpful, though. I am Sans. I'm curious. Sans is curious. Ian is curious. Oh God, I need to stretch. So we covered black holes today. I am so sad that you missed the black holes discussion. Ian, not Ian. Well, Ian also and Reese also. Tomorrow, I'll kind of repeat it so that you can. Fujino. Tomorrow, I'll kind of repeat it so you can hear it, and then we'll get into the grand unified theory. It's gotten cold in Boston today. It was warm. It was warm yesterday. Ugh. I'm feeling bleh now. I don't know. I don't know. Put this down. We can hang out. We can hang out. Oh my God. It's cold. It's so cold. Black holes. I think I need to find a little bit more material on black holes and cover that. I'm sad too. I was looking. Oh, thank you. No worries. We'll cover it tomorrow again. And we will then start grand unified theory. What time should we do it? Should we do it like 8 p.m. Boston time? 9 p.m. Boston time? Because you're going to be 4 hours ahead, I think. So what is a good time in the evening or night? Hi, Sachi Mama. Hi. 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 These bablas got their snacky. Got their snacky? Shona, baby? Hey, every day I might change my profile and name, okay? That's okay, Sans, Ian. We know you, Ian. Not to worry. If you want to change your profile and name every day, we're here for it, man. We're here for it. We understand. What breed is your cat? Hi, Axel. They are domestic short hair, is all I know. They're all pretty much like mixed, you know. Most likely I'll be awake at 1 a.m., 2 a.m. Okay, got it. 1 a.m. minus 4 is 9 p.m. Okay, sounds good. That sounds good. I figured I should do it a little earlier. 8 p.m., 9 p.m. of our Eastern Standard Time is probably a bit more respectable and decent of a time for most people. Excuse me. But I did get some people here. Oh, thank you. Thank you, Axel. Just came across your channel. Love it. I'm subscribing. Thank you so much. Please do subscribe. I will say that because I chose the time that I chose today, there were some people, I think from Asia, that were like new people that joined today that I have never seen before. And with the new people, it's always interesting because you never know what's going to exactly happen. And there were some interesting chatter, I suppose, in the chat. A little bit distracting, but fine nonetheless. I was fine with it. I was fine with it. Actually, I have to go up to the bathroom. I'll be right back. I'm gonna leave the phone here. Hi guys. Y'all can entertain our guests for a minute. I need to run up. I'll be right back. I'll be right back. But it was interesting. I think these Asia people, it was like well into the morning for them. So because of the time I went live, I got some new people that I never usually see. But that's the nice thing, like getting the new people is also good. But I wanted the regular crowd to be able to catch my black hole discussion. I think tomorrow I'll cover it again with a bit more context into black holes so that you don't miss the black hole part. It's a very interesting part. And then we'll continue grand unified theory, okay? So you won't miss anything, Reese. We will catch you up with the black holes discussion first tomorrow. Shona Moniz. These kitty cats are such shonas. Okay, babies, please don't do anything too bad. I'm gonna use the bathroom. Oh my god. Oh my god, you guys. Leave the mug here, did I? Nothing out. Good. Nothing out. Good. Off. 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 Vertical. 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 Off. 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 I'm just checking. These are things. Good. Yes. All right, I'll watch them. Ooh, nice. Thank you. Thank you. I'm still here. Okay, now I'm going up. crazy. I'm so sorry, guys. Oh gosh. Good job, everybody, watching the kitty cats. Aw, so cute. Hi, BJ. Hi. Sounds like she's shouting mom. What's that noise? They all followed me upstairs to the bathroom. Of course. Thank you guys for chatting. Thank you so much. Wow, I'm still reading your messages. Thank you so much for chatting. Okay, these kiddos are acting like they were not fed. I fed them multiple times. And they all were waiting just outside the bathroom. She's almost knocking. Yeah, watching them next to their autofeeder is a little bit like a suspense novel. I read about your dream, Reese. I had a strange dream. I was a worker aboard the Titanic. I was watching the stars and hoping the ship didn't sink. It was very cold and dark, and there was ice on the handrail. Wow, that's quite a poetic dream, Reese. Well, at least it didn't sink yet. Watching the stars is a good thing to do. I look with pleasure. Thank you, Axel. Dreams are so strange. Cats are the best. Thank you, Sans. Thank you, Ian. Oh, gosh. Yeah. Yes. Dude, I have a nightmare. Oh, gosh. Right now? Ian, it's getting late for you, right? Ian, didn't you say that you're 8 years old? It's a little late for you. It's quite not a good sign. They're scratching something. Yeah. They're not always good. Okay. Thank you for chatting once again. Thank you, Reese. Thank you, Ian. Thank you, Axel. Thank you for watching the kitty cats. So it's not your bedtime. Got it. Okay, we can stay up. You're right. I love to watch the stars. Sometimes I drive to a place with no light pollution to watch for shooting stars. Oh my gosh, that's my favorite thing to do. I don't get to do it as often as I want to, mainly because I need somebody to drive me. I need you, Reese. I need somebody to volunteer to drive me to a quiet place with no light pollution so we can see the stars. It's been a while since I've seen a night sky full of lots of. Oh my gosh, Baji! Look at Baji. Baji was trying to pick a fight with Suji. But I need a friend who wants to drive, basically to take me to a quiet place with no light pollution, like you're saying, this exact thing, man. This is what I need. A night sky full of stars, like to the point where you can see the Milky Way across the sky, you know? Like maybe at the... I think the last time I saw the Milky Way might have been a few years ago at the beach. Like it was a very quiet beach, or sorry, a very quiet and dark beach, like quiet except for the ocean. And it was at the Outer Banks, actually, in North Carolina. And I saw the Milky Way there, and I saw the Milky Way, of course, in Hawaii as well. Basically, like, if it's dark enough where you can see the Milky Way and you can see a night sky full of stars, that's, like, amazing. I would love to be your driver. Please, yes! We need to do an English countryside, or a British countryside. I don't actually care if it's England or Scotland or What's the other one? Ireland. Wales. I'm up for anything. It just has to be a quiet countryside, very dark, less light pollution, and of course, safe place, hopefully, where we can go and see a night sky full of stars. Sans or Ian is saying, dude, I go to sleep at like 3 sometimes. Yeah, dude, me too. I have also been a bad kid. Not that I'm a kid anymore. But I think even when I was a kid, I was a little bit like this, a bit of a night owl, you know? There is so much more peace at night. Nobody's trying to get a hold of you, usually. All the business hours types of people are asleep or doing whatever they're doing. And here we are doing a nighttime live. I used to read a lot of books too when I was young and like up at night. Sometimes when I go to sleep, I look out the window and I see some planets. Ooh. Ian, remind me where you're joining from. If you want to. You don't have to. I used to stay awake all night reading. Wow. When I was little. Ulysses, that's right. I forgot. Sorry, Ian. I did know that. I used to stay awake all night reading. That's like me, Reese. We're the same. Ulysses, that's right, Ian. I think I'm seeing you after a while, Ian. I feel like you were joining my Saturday Sunday lives, but then I didn't see you for a while. So I'm glad you're here with the new profile and everything. Yeah. Yeah. What type of books do you like reading, Reese? Or did you used to read? Oh, no worries, Ian. Happy that you're here. কি হয়েছে সোনা? Fuji Baba? Fuji Baba is saying words. I used the little blue light on my watch to see the words so I didn't have to put the light on and get into trouble. Oh, wow. Fuji! Karna Shona? Hey, Baba. Look at what he's doing. He's getting into so much trouble. I'll give you a little bit of a snack, but Fuji, you've already had some. Fuji, ne? No, Fuji. Come, Swaji. Suji, Mama. Okay, fine. I'll give it to you here. Oh my gosh! Enid Blyton, that's who I grew up reading. I read every Enid Blyton book. And Roald Dahl. Not as much Dahl, but I literally read like all of the Enid Blyton books. Like all her adventure and mystery series, her like Twins at St. Clair's, Mallory Towers, you know, all the boarding school types series that she wrote, as well as all the like adventures of those like kids. What were they called? Five Finders? Oh my gosh, you just reminded me of my whole childhood. I read like all of her books growing up. Basically, when I was little enough where I read her books and then I finished all her books. And then I moved on to more like Agatha Christie, Sherlock Holmes, Conan Doyle's, like all of those types of books as well. And then Harry Potter's, you know. I probably have some Enid Blyton even now. But that's like what I really, really read. Last Firehawk is a good series. Have you guys read The Last Firehawk? I have not, Ian. I have not read that one. I loved Blyton. I remember one about a land with a very clever, wise people with huge heads. It was funny. Ah, wow. Look at us. We read the same author growing up. Goodness. Goodness gracious. I'm charging my phone, but I'm still here, so we can still chat. That's great. Same author. Fuji Baba, কেন এরকম করছো শোনা? এরকম করে না বাবু। ছেড়ে দাও ওটাকে। Let's not try to break this auto feeder. I'll plug it in again. Fuji. No babies. Chalo. ছেড়ে দাও বুবলাই। Okay. Didn't you just get some? Didn't you just get some? They're being difficult, the children. Lighten. I don't read much these days, sadly. No, I know what you mean. When you're, there was a time, like I'm reading a lot more now, but basically, with like regular school, job, all this stuff, it can be kind of hard to keep up with reading. But it really is the best hobby. For me, at least, I like it a lot. I liked Stig of the Dump also. I read that many times. And a book called Holes by Louis Sacher. I read that one night and went to school the next day after having no sleep because I could not stop reading it. And I read a lot of science books and books about how things work. Ooh! Yeah, that makes sense. That makes sense. Me too. I liked, I liked adventure, mystery, science, that sort of stuff. Physics. Fuji. Karna. Shona, not a good thing. Not a good thing. But I understand when you're like working a regular job and stuff, it's a lot of time spent with work, so you can kind of fall out of reading. I'm getting back to it a lot more now, but there were probably years when I read so much less. When I grew up reading all the time, like I read books all the time, like you're saying, like staying up all night and finishing something. That's how I used to be too, a lot. Because I want to learn how sharks are immune. Oh, you want to be a scientist? Oh, that's awesome. You should be, Ian. That's great. I've always loved science and physics, not so much chemistry though. Yeah. I think I liked physics more, but I was better at chemistry actually when I was in high school. And I took both in college. So, but then I didn't finish my degree in chemistry. I finished it in physics because it was going to cost more money to keep doing classes. You should totally do that, Ian. That's a very good idea. Ian's gonna cure cancer. I believe in you. Love it. Love that idea. Put this down, but I'm still here. Thank you so much. Of course, Ian. Thank you for your future work in cancer research. And I'm glad that you're already getting started. Reese, do you have to work tomorrow? Or I guess it's Sunday. Do you have to work on Monday? How's the day looking for you tomorrow? Just pour myself a drink, actually. So what is your guys' favorite thing to do? I got all A's in the sciences at the end of high school, and then I went to do electronics college class after, but the course was canceled on the first day. Oh no. So did you ever do electronics class after all? What is my favorite thing to do? I think I like going to the ocean a lot. I love the ocean, like a walk by the ocean, or what we were mentioning earlier, looking at the night sky, like star watching. Just walking in general. I love walking, like in nature, like for a hike, in a sort of a woodsy area. Breathing, eating food. I love food. Food that someone else has made, hopefully, because I'm not a big cook. So I like spending time with my kitty cats, my kiddos, snuggling the kitty cats. Oh, sorry. Whoops. Didn't mean to show that. So yeah, I like walking, reading, eating, sleeping. Ooh, and I like watching movies a lot too. I don't watch movies as much as I might have in the past, but I do like movies. I like to play snooker. I don't think that's really a thing. Is that like pool? Like billiards? Like the table with the balls that you hit with the stick? At school, when I get mad, I break pencil. Oh. What are some of your favorite movies? Okay. All right. Well, Reese, I hope you have all night. A lot of the movies that I really love are Indian movies. I don't know if you would know them. They're from the Hindi film industry. I'm a big fan of the Hindi film industry. So if you're not really into that, you might not get the vibe of what I'm saying. But I love big romantic drama type movies. Yes, Bollywood movies. Bollywood is like the yeah, exactly. Yep. Big romance and drama type Bollywood movies are my favorite. Actually, I just watched a movie on Netflix called The Crew, and I liked it. So I think maybe not anymore. Like maybe growing up, I used to really like the big romance drama type of movies. There's like a movie called Devdas that came out when I was young, and I loved it. It was about this like big, sad love story. But now, I mean, I still kind of like the movie because it's like part of my childhood. But I kind of think that the movie and this, whatever. I don't know. As an adult, I might have different thoughts about it. But today, I finished a movie that took me like 3 or 4 days to finish because I only see a little bit and then I have to do some work. So I don't really finish movies in one sitting nowadays. But I finished this movie finally called The Crew on it's on Netflix. I don't know if you have Netflix. Could give it a shot. It was funny. I haven't seen any Bollywood movies, sadly. Hollywood, you mean? No, I mean Bollywood. So, Ian, Hollywood is like LA, West Coast America, Hollywood. It's a place, right? So, our American movies are sometimes called Hollywood movies. The Hindi film industry in India was given a nickname Bollywood. So, a lot of people call it Bollywood. It's as a nickname because we have a city called Bombay there with a B. It's actually been renamed Mumbai. I like comedy movies. That's a good thing, Ian. Liking comedy is honestly great, and sort of like having comedy in life in general is a good thing. I have Netflix, but I tend to flick through the movies for hours and never actually choose anything. Oh gosh. Well, Reese, if you need any help with that, I can make some decisions and tell you what to watch. But yeah, it's a lot of options, right? I understand the issue with that. Like it's like there's so many options. Sometimes I usually have Netflix canceled actually. Like I don't pay for Netflix for too long. There's like 3 or 4 things that I want to see that I might see and then cancel it because I don't want to be paying for it if I'm not gonna use it. Um, what is a fruit that has passion? Passion fruit? I don't know. But yeah, I just watched this movie called The Crew. Passion fruit. Yes, that's what I said. Uh, I saw that. That was funny. So I've grown up watching a lot of Bollywood movies, and it's a whole thing. It's a whole world of its own. So what is The Crew about? So it's about, like air hostesses on a plane, like the crew of a plane, cabin crew. So these people, oh, I see. These people, look at Suji. These people are working on a plane and they have like financial problems and they want to, they get into like smuggling gold and they realize that like people that are higher up in the airline company are smuggling gold and getting rich to richer and they're like still struggling financially and they have all these like issues, but it's like about 3 women who are working as the cabin crew and they kind of try to do these other side hustles and like how that all goes with the smuggling. That's what The Crew is about. It's funny. It's like a comedy, I liked it. BJ. Yeah. Watch it if you want. If you have it in England, you can try to see if you have it and see if you want to try it out. It has subtitles. BJ, how are you? BJ, tell us your favorite movie. BJ is from South Korea. It sounds good. Thank you. Have you seen East is East? No, I have not. Is it good? East is East. It's about an Indian family living in England. Oh, have you seen East is East? Is it about the guy who like cooks? I might have seen it on a plane, but I don't know if I've seen it, or if I've just seen a trailer. It's very funny. Okay. Okay, good to know. I bet it'll be on a plane again when I fly. I'm good. I like Jim Carrey movies. Yes. BJ. Me too. I love Jim Carrey. He's so funny. It's nice to see stuff that is funny. His expressions are so spot on. Like he has so many funny expressions. Jim Carrey. Love him. Okay, but I'm gonna have to check it out. East is East. Oh, good. Yeah. But BJ, you can also recommend some like Korean movies to us. I've seen a few Korean movies. If you have any recommendations, let us know. Let us know. It's sort of about the father of the family and his controlling of the rest of the family. They don't want arranged marriages and he's pushing them. Ah, I see. Got it. Yeah. Yep. That can it's like half comedy, half very serious. I see what you're saying. Yeah. Got you. The Crew is like mostly comedy, maybe a little bit serious. And I really like the actresses who play the characters in The Crew. So it's also partly that I grew up watching some of those actors, you know, like the women that are the main roles in that movie. So, and they're really, really good. So that's why I liked it a lot. I think it has to do with the kind of being immersed in that culture overall and enjoying it as part of that. I think it's groundbreaking in the way that it helped British people understand and respect the Indian culture more. Oh. Oh, interesting. That's cool. But didn't the British people have enough time to do that in India? Oh, dear. You know, when they were living there, they should have learned more from us, I feel, in some ways, in many ways. But I'm glad that the movie helped. Some British aren't very welcoming of other faiths and religions, etc. Small minded and borderline racist. That's like everywhere, you know. Some people can be very closed off. That's. But racism was sort of institutionalized here in the 60s and 70s. Oh, really? I don't think I know about the 60s and 70s in Britain. My recommendation is an old movie. I don't know, you can't watch it. It's called No Manners in 2002. Okay. Well, I'll ask around about it. I have friends who might be able to find it for me, BJ. If it's a Korean movie, I'll tell them that it's a Korean movie. Can you find it? I have friends who can probably figure it out. Huh. I did not realize that racism was institutionalized. I'm in my 30s, but I know about the way things were back then. Oh, that's interesting. Thank you for sharing, Reese. Oh, good. Someone of my age, then. I can speak different language. Which ones, Ian? Espanol? English? Portuguese? Which one? I actually don't think I know too much about the 60s and 70s beyond. I know a little bit about India in the 60s and 70s and about America. I don't think I know too much about Britain in the 60s and 70s. Interesting. It's a Korean movie. There are many famous actors in their young age. That means hi. Oh, hi, Ian. Okay, No Manners. All right. Korean movie called No Manners from 2002. Got it. I'm gonna have to find it. There's a movie called This Is England, which shows a bit about how things were. Okay. Sounds good. Sounds good. We'll check it out. I'll have to see if I can find it. The music of that era, sort of brought cultures together, the reggae, etc. Got it. East is east. Cool beans. Interesting discussion. Thank you for everybody's contribution and talking about the movies that you know and sharing about your culture. Oh my goodness. I'm gonna sit down now. There's a scene in East is East where yes, I will recognize it. When a famous Bollywood song or something, which there's many of, like if I just hear the beginning of it, I know which song. If there was like a quiz on Bollywood, I'll probably win, or at least do well. That's one topic I know about. There's a scene in East is East where the family go to see a Bollywood movie. I am sure I would know which one. Maybe you will recognize it. It seems like a famous one. Let me guess. Was it DDLJ? Dilwale Dulhaniya Le Jayenge? That's like the most famous movie in Bollywood. Hi in Korean is people I like. Hi is in Korean. Oh, thank you, BJ. Yes, please confirm what is hi in Korean before we learn the wrong thing. I love some of the Indian music in that movie, especially where the daughter, Nina, is dancing with a sweeping brush. Oh gosh, yeah. Okay, so I've definitely not watched this movie then. I have not seen a scene where anybody is dancing with a sweeping brush. Okay, East is East. Gotta see it. Hi is young? Is an young, maybe? Hold on, I'll try to find out what it's called. I am going to bed, so Reese, don't tell me. I'm gonna keep guessing, so don't tell me the movie name. Dilwale Dulhaniya Le Jayenge, DDLJ, that's my first guess. If that's not it, then just say no. Then I'll guess the next guess. Suji Mama! Oh, Suji's doing gymnastics. Look at that. Hi, Suji baby. Shona. Yes, right. Japanese? BJ, do you understand Japanese as well? Goodness. Ian, I love that you're practicing other languages here in the chat. I do appreciate this diversity. Oh boy. What a lovely chat. I thought I would see none of my friends when this live started. Except for, I did see some of my friends earlier on. But then more of you came along. So the song is Inhi Logone by Lata Mangeshkar. Oh, I don't know if I know this song, but it's coming to me kind of. I know some Japanese letters, not every haha. Inhi Logone, Inhi Logone. Is it like that? Maybe I don't know the song. The song is Inhi Logone. Well, I know Lata Mangeshkar. She's extremely legendary. Yeah, like that. Oh my god! Inhi Logone, Inhi Logone. I don't know it. I don't know anything further though. It's not really a song I know very well. Or I would sing it for you. I like singing. Lata Mangeshkar. I don't think that's like one of her most famous songs. It's pretty old. Is East is East kind of old? Is this some like really old movie? Because this song seems old. Claire, I subbed your channel. Thank you, Claire. Thank you so much. Love it. Welcome, welcome. Claire, I feel like I've seen you before on the live. How are you doing? Feel free to say something more. I think the movie is from the 90s, but it is set in maybe the 60s. Ah, okay. I see. Okay. Oh, I see. That's why you were saying that it kind of makes sense with the 60s and 70s culture in Britain. Got it. I'm from the 90s, another whole century. Or sorry, millennia, right? I'm from the last millennium and century. I see. I think I did not see this movie. If I was very young when the movie was released, I might not. I'm from the 80s. Oh, wow. Good. Actually, that's kind of funny. 89, oh my gosh, that's so funny. I think I have like 2 closer friends in Boston, and they're both 89. They're also from the 80s. Wow. I think the movie is, or sorry, I already read that. What is this, 2016? You're from 20, you were born in 2016, Ian, because you're 8. Got it, Ian. Good for you, Ian. That's a very good thing, Ian. Born in 2016. Wow. The 90s were the best years. Yes. I slept past 5 a.m., so I gotta go siesta. Haha, have a nice day, guys. Yes, have a nice day, BJ. You slept past 5 a.m., as in it was late when you went to bed. Got it. Okay. Good night. Have a good nap, BJ. I know it's morning for you in Korea. 90s were the best years. Yes. So there is an actor that like everybody likes a lot. I mean, he's like worldwide known. I mean, you might even know him because even the people that don't really watch Bollywood know this guy, right? So his name is Shah Rukh Khan. If you don't know him, well, he's like the biggest star in the world. So he started his career in the 90s and he actually started as sort of like these villain roles and these other different types of roles. And because I was so young then, I didn't see his first movies. And later on, he became more of a romantic hero and like this. He did like these really big romantic drama type movies, like I was saying, which I became a fan of. So I used to think that he's kind of like a hero or an actor who does that. But then I realized later on that he had all these other movies in the beginning that were like villain roles. And yes, the 90s did have a lot of different content like that that was interesting. I've heard of him, but I don't think I've seen his movies. That's okay, Reese. You know, I make all my friends watch at least some Bollywood movies. So some of these friends that I've met here in the US who had not watched Bollywood movies are now well acquainted with Bollywood. I don't think I've seen many romance movies except Beautiful Woman or Pretty Woman. Ah, Julia Roberts. Got it. Julia Roberts, or sorry, Pretty Woman, I guess it's a romantic movie. I mean, even more romance than that. Like big, tragic, huge love stories. That type of stuff is what I used to like a lot when I was younger. Uh, Pretty Woman. But it's a good movie. It's funny. I feel like I should let you sleep now. Thank you so much, everybody, for chatting. Thank you, Ian, for joining and telling us so many letters in Japanese and other languages. Reese, thank you so much for chatting. Missed you at the beginning of the live, but I'm going to cover black holes again tomorrow and then do my discussion. Yeah, I know what you mean. It's not very romantic apart from the at the end when he climbs up to see her. Yeah, 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 yeah. Other than that, like it's a comedy sort of, right? So I do like the movie in general. I think nowadays I'm much more of a comedy type of person. I don't really need the movie to be like a big romantic drama for it to be interesting. Axel says, it's beautiful. Thank you very much for sharing. Thank you, Axel. Thank you. Thank you, thank you. Thank you for being here. Reese, Axel, Ian, do you guys have to go to bed? You should probably go to bed now. Get some rest and be at the live tomorrow. Yes? Oh my god. Baji's on my back right now, making biscuits. I don't want to move because then it'll disturb him. Guys, guess what this means. Bye. Does it mean bye? I hope to catch your live tomorrow. Okay. Awesome. So tomorrow I'll try to go live a little bit earlier so that it's not so late for you, Reese. And also I think it'll be helpful so that in America too it's not getting too late for people. I've slept 3 hours or so. I'll be awake for hours now. Oh, wow. So you just need 3 hours of sleep? Goodness. That's not a lot of sleep. Yes, it does mean bye. So, guys, I can't move because Baji's on me now, on my back. And by back, I really mean my butt. Oh my god. Baji! Oh. I'm stuck. I only need 1 hour of sleep. Oh god. Ian. I hope you have a wonderful night's sleep. Thank you. Thank you. Thank you. You too. Try to get some more rest. Sorry that this live interrupted your sleep or something interrupted your sleep if you were already sleeping. Hopefully you get more sleep. I don't know why I can't. I can't go to sleep. Wow. Ah. I'm getting so warm now because Baji is on me. It's like a sweater. Oh, wow. I don't sleep much. I was trying to stay awake to watch your stream, but I nodded off. I did some painting in the house today. Maybe it made me tired. Yeah, that's a lot of work. You should sleep more, Reese. Why don't you get some sleep now so that you can be up and at my live tomorrow night? That's enough energy to stay awake for 2 days. Oh my gosh. Thank you for trying to make it to my live. But yeah, get some sleep now. It's still early for you so that you can have a good Sunday and we can catch up at my live tomorrow night. Have a good night. Sweet dreams. Okay. Bye. See you tomorrow. See you tomorrow, my friends.